We can tell you right now with total confidence that solar cycle 25 reached its peak in October of 2024. We can tell you the sun has been quieting down ever since, cooling off, settling into its expected decline. And we can do something even more astonishing than that. We can tell you, centuries in advance, the exact second the moon will slide in front of that star, and the exact strip of Earth that will go dark beneath its shadow. On August 12, 2026, that shadow arrived exactly where the mathematics said it would. It swept across Siberia, across the ice fields of Greenland, across Iceland, and then, for the first time in 121 years, across Spain. Crowds gathered along the path. Telescopes were angled skyward. Eclipse chasers who had flown across the world for this exact moment stood shoulder to shoulder with locals who had never once seen their sky go black at midday. By every model, this was supposed to be the quiet version of totality. The sun was past its peak, past its violence, sliding toward its slumber. Scientists expected a thinning corona, the star's outer atmosphere, faint, subdued, an afterimage of the far more dramatic eclipse that had blazed across North America just 2 years earlier. They had their instruments ready, their calculations finished, their expectations set. For less than 2.5 minutes, the moon would block the sun completely, and in that narrow, precious window, they would get their answer. They thought they already knew what that answer would be. They were wrong, because what emerged from behind the moon's shadow that day was not the calm, fading star the numbers had promised. It was something else, something that didn't fit the decline, something that, for a few fleeting seconds over Spain, made even the scientists watching it go quiet. They had come expecting an ending. What they got was a question. To understand what unsettled them, you have to understand what they were actually looking at. The sun's surface, the blazing disk we're taught never to look at directly, is not, in fact, the hottest part of the star. Surrounding it is a halo of plasma called the corona, and under normal circumstances, it is invisible, drowned out entirely by the overwhelming brightness of the surface below it. Only in the brief, unnatural darkness of a total eclipse, when the moon blots out that surface completely, does the corona reveal itself. A crown of fire visible to the naked eye for 2 minutes, maybe less, once every year or two, if you happen to be standing in exactly the right place on Earth. This is the only reason scientists still chase eclipses in the 21st century. It's not superstition, it's opportunity. A narrow keyhole into a part of our star we can study almost no other way. And on August 12th, what came through that keyhole did not match the forecast. Instruments built to capture a fading, thinning corona instead recorded something far more structured, far more active. Streamers of plasma extending in complex, tangled formations, the kind of activity researchers associate with a sun near its violent peak, not 2 years into its decline. The data sat in an uncomfortable in-between, too energetic for a calming star, not chaotic enough to match 2024's outright maximum, a reading that didn't cleanly belong to either chapter of the solar cycle. Heliophysicists have a name for the deeper mystery hiding inside this discovery. It's called the coronal heating problem, and it has haunted solar physics for over 80 years. The sun's surface burns at roughly 10,000 degrees Fahrenheit. Its corona, the thin atmosphere stretching millions of miles above that surface, somehow reaches temperatures hundreds of times hotter. By every basic law of thermodynamics, that should not be possible. Heat is supposed to fade as you move away from its source, not multiply. No one has ever fully solved why the outer edge of our star burns hotter than its core. And in 2026, for a window lasting less than 150 seconds, that unsolved fire chose to burn brighter and stranger than the models allowed for. Teams on the ground in Iceland and Spain worked in near silence, aware they were capturing something that might not repeat itself for years. Every second of totality was borrowed time. Every frame of data, a fragment of a puzzle that wouldn't sit still long enough to be fully measured. They got their images, they got their readings. What they didn't get was an explanation. Here is the part of the story that turns this from a curiosity into something with teeth. An unpredictable sun is not just a puzzle for physicists. It is a direct physical threat to the world we've built. The corona that flared brighter than expected over Spain is the same region of the sun responsible for 2 of the most dangerous phenomena in our solar system: solar flares and coronal mass ejections, massive eruptions of charged plasma hurled outward at millions of miles per hour. When one of these eruptions is aimed directly at Earth, the result is a geomagnetic storm. And geomagnetic storms are not abstract. They are capable of disabling satellites, corrupting GPS systems, and, in extreme cases, collapsing entire power grids. This has happened before. In 1859, an event now known as the Carrington event sent a solar storm slamming into Earth so powerful that telegraph wires burst into sparks. Some operators were electrocuted at their stations, and auroras lit up skies as far south as the Caribbean. At the time, it was a spectacle, a curiosity for a world barely wired with electricity. We are not that world anymore. A Carrington-level event today would not simply light up the sky. It would tear through satellite networks, banking systems, air traffic control, hospital equipment, and national power grids simultaneously on a planet with almost no functioning backup for a world without electricity. Some estimates place the potential economic damage in the trillions of dollars, unfolding over months, not days, as damaged infrastructure struggles to recover. And this is precisely why an unpredictable sun is so unsettling to the people who study it for a living. Our entire modern civilization operates on an assumption that we can forecast solar weather, at least broadly, the way we forecast a hurricane, that we'll get warning, that the models will hold. The eclipse of August 12th quietly challenged that assumption. A star that was supposed to be calming down instead showed behavior sitting outside the clean boundaries of the model. Not catastrophic, not yet, but a crack in the confidence that we understand this star's rhythms as well as we claim to. Because if the sun can behave this unpredictably during a routine phase of decline, in full view of our best instruments, the uncomfortable question becomes obvious. What is it capable of when no one is watching closely enough to notice? For less than 2.5 minutes, on one afternoon in August, a small number of people stood on a strip of land stretching from the Arctic to Iberia, and watched something our best instruments couldn't fully explain. Then the moon moved on. The light came back. The corona vanished, swallowed once again by the ordinary blaze of the sun's surface, hidden until the next eclipse gives us permission to look. Sit with the strangeness of that for a moment. We can calculate, centuries in advance, the precise second a shadow will fall across a specific patch of Earth. We can name the towns in Spain that would go dark, down to the minute, before most of the people standing there were even born. And yet, in that same sliver of time, staring directly at the very phenomenon we traveled across the planet to witness, we still cannot fully explain what makes its outer atmosphere burn hotter than the star beneath it. That is the paradox sitting at the center of this story. Total mastery over prediction, total humility in the face of explanation. The sun is not a solved problem. It is the one object in our solar system every living thing on Earth depends on completely. And it is still, after all our centuries of watching, capable of surprising the people who study it closest. This particular alignment, this shadow over this stretch of Earth, will not happen again for well over 100 years. The scientists who stood in Spain that day will likely not live to see it repeat. Whatever answers still wait inside that brief window of darkness will have to wait for someone else. A future team, with better instruments, standing in the same borrowed 2 minutes, asking the same unanswered question. We live our entire lives in the light of a star we have never fully seen. And every so often, for just long enough to remind us, it lets the shadow fall, just to show us how much of it still remains unknown.